Hey, fellow mathers, we've got exciting news for you.
Yep, registration for the free Math is Figureoutable Challenge is now open.
Oh, get ready for a fast paced learning experience where you'll learn the real meaning of fluency and how to build it in your students. Find joy in teaching math and engage in super cool mathing.
There'll be a very special guest, free downloads, prizes, and more importantly, a high energy, engaging 3 days of sessions.
Join us for 3 1-hour sessions from September 3rd through the 5th, 7 p.m. Central Time. Register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the episode.
Hey, fellow mathers, welcome to the podcast where math is figure-outable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figureoutable, we are on a mission to improve math teaching.
We know that algorithms are amazing human achievements, but they are terrible teaching tools because mimicking step-by-step procedures actually traps students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we help you teach mathing, building relationships with your students, and grappling with mathematical relationships.
Y'all, thanks for joining us to make math more figure-outable. Da-doo-doo. All right, Kimberly.
Hello. What you got today?
Should we do some math?
I would love it.
I would like to do some math.
Does that mean I'm doing math?
Yeah, that is actually what that means.
Okay. Kind of figured.
Okay, so we have a member of our coaching group who raised a question the other day and got me thinking. So, Brandon, thank you for raising the question. And it got me thinking about the ways that I have done some things. Anyway, I don't want to front load it too much because I kind of want to talk about it afterwards. But
Okay.
Brandon Pelter, thanks for getting me thinking. And a couple other people have mentioned some things. So let's just do a little bit of math, and then I'll kind of talk about how that relates to kind of how they were poking me. Okay, so I've mentioned before that we have a favorite recipe. Oh, in fact, funny. So I was in Virginia not too long ago, and a great group. And a gal, first of all, was like, shout out to Kim. She's like, where's Kim? Where's your sidekick? Like, oh yeah, she's not here.
I really do think you need Kim on a stick. You know, like a picture of my head, like they have at sporting events.
I could take a life size
Gosh, no.
flat and just carry it around with me.
No.
But Kim on a stick. Okay, I could pick. I could wear our podcast shirt. We have a podcast shirt where it's
could.
the pencil and the pen. That would be cute. Anyway, this person or one of the people said, "Do you really have a chocolate chip peanut butter cookie recipe?" And I said, "Absolutely." Now, is it in the ratio that I say? Maybe or maybe not, but it's close.
Do you know I haven't ever had your peanut butter chocolate chip cookies? Just
What?
the chocolate chip ones that you used to bring to school, like
Would
forever
you-
ago I got.
I did take chocolate chip oatmeal chocolate chip cookies to school. I always take those to the school to the teachers before school started. Do you like peanut butter chocolate chip cookies?
I mean, they're okay, but I would not turn down your chocolate chip oatmeal ones.
Okay, well, so next time I make, we have a new family member.
I don't get it anymore.
We have a family member that was just diagnosed with celiac, so I'm not doing a lot of baking with flour these days.
My family's not.
So I could make them and then you'll eat them all. You'll take them 100%. Off my hands.
I don't even really love sweets.
See, that's why I wouldn't have like pegged you for you want cookies.
Okay, on to the recipe.
Okay, so Kim, what if my favorite peanut butter chocolate chip cookie recipe says that I need 2 cups of peanut butter for every 3 cups of chocolate chips, because you should have a lot of chocolate chips in any cookie.
Yep.
And a cookie with raisins in it is a muffin, just to be clear.
I would not be sad about those either.
Well, I'll let you eat all the muffins in the world, and I'll eat all the cookies, which means they have chocolate in them.
Muffins have chocolate sometimes.
No, then it's dessert. It's not a muffin. Then it's like if it has chocolate in it, then it's a cupcake.
I want lunch. Can we move on?
Oh, you're hungry?
I haven't eeten yet.
Oh my gosh, it's late in the day for not. Okay, we better. Wow, I want to hand Kim some food.
Cookies. Bring me cookies. Okay, this is gonna be a rough episode. I can tell.
Kim, if it takes 2 cups of peanut butter and 3 cups of chocolate chips in my recipe, what if I walk into my pantry and I have 4 cups of peanut butter? How many cups of chocolate chips do I need?
You need 6 cups of
because
you have twice as much peanut butter, so you need twice as much chocolate chips.
Okay, cool.
Twice
What
as
if I
many.
only twice as many? What if I only had 1 cup of peanut butter in my pantry and I need 2 cups for every 3 cups of chocolate chips? How many cups of chocolate chips?
1.5 cups.
Because
I looked back at the 2 to 3,
mhm,
and now you have half as much of each
of
ingredient.
each of them, yeah, it's half as much. Cool. What if I am baking for I don't know, Kim's family,
Mm-hmm.
maybe your whole extended family, and I know that I've got 7.5 cups of chocolate chips. So not peanut butter anymore. Now I've got 7.5 cups of chocolate chips. How many cups of peanut butter would I need in order to make that recipe with those
I
seven
think
and a
you
half?
need, yeah, I think you need 5 cups of peanut butter.
And you're welcome that I
Mm-hmm.
kind of
That
gave
was
you some
nice. Appreciate
value
it.
because you had you had the 6 cups of chocolate chips. You had 1.5 cups of chocolate chips. Am I
Yep.
right? You just added those
Yep.
together.
Yep.
So then you added the corresponding 4 cups of peanut butter to 1 cup of peanut butter, and so you're saying 5 cups of peanut butter would need 7.5 cups of chocolate chips. Cool. What if I walked in the pantry and I had 10 cups of peanut butter? How many cups of chocolate chips?
I need twice as much as when I had 5 cups of peanut butter.
Okay,
So 7.5 doubled is 15.
cool. Got anything else? Because I don't know if you've been writing. If I was doing this in class,
Oh yeah, I had the 1, so I could do 10 times as much.
so like 1 cup of peanut butter times 10 would give you the
Mm-hmm.
10 cups,
Yeah.
and that 1 cup of peanut butter needed how many cups of chocolate chips?
1 cup is 1.5.
One and a
So
half. So 1.5 times 10. Ooh, and here's an opportunity where now I have some nice place value on the board
mm-hmm.
where a lot of kids are going to do what you did, double the 5 cups and double the 7.5 cups. And so now I'm really clear that 10 cups of peanut butter is 15 cups of chocolate chips. And now I can high dose kids with the place value pattern of what happens when you multiply by 10 with decimals. I'm not butt cheeking. I'm not just moving the decimal, but I'm actually watching that 1.5 shift in the place value system to 15 when I scaled
Mm-hmm.
it times 10. And so does that make sense that we're kind of feeling it two ways? We're not feeling the place value pattern, but we're really clear that I can go from the 5 to 10, so I can double the 7.5 to 15, and then I can notice the place value pattern. And I go, okay, it really is true. This shifting thing that happens when we multiply by 10. Cool.
Yeah.
What if I walk in the pantry and I'd like to make peanut butter chocolate chip cookies, but all I have is 1 cup of chocolate chips. That's all I got. How many cups of peanut butter do I need to have in order to you're not happy with that one?
You're pretty sad. So,
Because I'll only be able to make
it's
enough
like 1
to bring to
cookie, 2
Kim.
cookies. That's okay. I'm not sad.
Wait, you want a cup of chocolate chips for 1 cookie? That's a lot of chocolate
Oh,
chips for
that's a
one
lot.
cookie.
I
You
don't
don't
know
even
how many in your recipe.
you don't
It's
even
been a
like
while.
chocolate chips. Does
Okay.
everybody know when we go snack shopping, I go for the chocolate and Kim goes for the what do you even go? Gooey? Gummy?
I
You get a
mean,
gummy.
now just chips. Like I
Um,
love chips.
okay, so that's like a
Salty.
snack. Is that a treat too? Is there a difference between a snack and a treat?
Well, I think you're referring to I used to get like gummy, sour, chewy. I just
Yeah,
don't really have any of it anymore.
really?
Yeah.
Ever?
No.
Huh. Okay.
Um, so I'm looking at my ratio table.
Is that because you got healthy or fuddied it?
It's not worth it, I guess. I don't know. I'd rather eat chips, salsa, queso, real food. I don't
Real
know.
food. All right, all right, all right. Okay. 1 cup of chocolate chips. How many cups of peanut
Yeah.
butter do we need?
So I first looked at the 1.5 cups of chocolate chips
Yeah.
and I compared that to the 1 and I said, okay, 1.5 would be 3 halves of the 1 that I need.
Like 150%.
Yeah.
Okay. Okay.
And so I thought, well, if I want to get from 1.5 to 1, then I only need 2/3 as much.
You need 2/3 of 1.5. 2/3 of
hmm
1.5 is 1.
And then I went on
How
the
do
other
you know
side
that?
because there are 3 parts of 1.5, a half, a half, a half.
Okay.
And for 1, I use 2 of those parts. So 2 of the 3 parts of 1.5.
It gave you the 1 cup.
So
Nice.
then on the other side for peanut butter, I need 2/3 as well. So 2/3 of 1 is 2/3.
Because I gave you 1 cup of chocolate chips and you're like, I need 2/3 of it. 2/3 of, and that's why you said 2/3 of 1.
Oh, I guess I could have just gone from the 3 to the 1 and divide that by 3.
Okay, so and you're referring to the original 3. So we
Yeah.
had 3 cups of chocolate chips. You're
It's
like,
too
how can
far
I
away.
get from how can I get from 3 to 1 multiplicatively? You could divide by 3, and then you would scale the 2 cups of peanut butter. You would divide that also by 3. Well,
Yeah.
Kim, how do you know what 2 divided by 3 is? 2 cups of peanut butter divided by 3. That seems complicated.
No, that's just 2/3
So 2 cups divided
divided by
into
3.
3 portions is 2/3 of a cup. And that is a big idea that we need to help students develop,
Yep.
not just tell them that division is fractions and fractions are division, but actually, like in this case, like really think about it and reason. And that will help them do what you did, which I think is more complicated. The 1.5, or sorry, the 1.5 to 1, thinking
Mhm.
about 2/3 of 1.5. I mean, we want kids to be able to do both of those. Yeah, nicely done. So now we kind of have some relationships up here. We've got 2 to 3, 4 to 6, 1 to 1.5, 5 to 7.5, 10 to 15, 2/3 to 1. And all of these are expressing an equivalent relationship. So we would say that all of these are equivalent ratios. And so we could have a lot of proportions here. We could have, this is a proportional situation. So when we scale one of them, we scale the other by the same, sort of scaling in tandem. And we started with a non-unit rate of 2 cups to 3 cups of
Mhm.
2 cups of chocolate, 2 cups of peanut butter, 3 cups of chocolate chips. I could then ask kids, hey, what if we were to graph those as ordered pairs? Would there be a pattern? Kim, if you were to sketch a graph, could you just maybe, where would the first point be? Like two cups of peanut butter to 3 cups of chocolate chips.
2, 3.
So you'd go over 2, up 3, and plot a point, and then over 4, up 6, plot a point. And if you let's see, over 1, up 1.5, plot a point. If you were to do that, would there be any pattern with those points?
They'd all be on a line.
So then I would want to ask kids, what line do all of those points lie on? Is there something I can do to figure out the number of cups of chocolate chips I need given the number of cups of peanut butter? Like I just put an X and a Y in the table. So right now it's X cups of peanut butter to Y cups of chocolate chips. And I'm sort of curious if I just told you some random number like 100, I've got 100 cups of peanut butter. Could you do something to that 100? Like maybe let me back up a little bit. You just went from cups of peanut butter to cups of peanut butter, and then you scaled in tandem to the cups of chocolate chips. Or you went from cups of chocolate chips to cups of chocolate chips, and you scaled in tandem from cups of peanut butter to cups of peanut butter. Now if you could see me, I'm vertically kind of moving my hands in these scaling like movements, motions. But now I want you to consider kind of the relationship across the table. I was kind of moving up and down my table because I had a vertical table. Now
Mhm.
I'm asking you to consider the relationship across. If I just gave like 100, what could you do to the 100? Like you could scale from another cups of peanut butter, but I want you to like just between peanut butter and chocolate chips. What are you thinking?
So I think we had that with the 1 to 1.5,
Okay, say more.
that you can multiply the x, whatever the x is that you give me, times 1.5 to get whatever the y is.
So let's check that out. If I give you 2 cups of peanut butter, what's one and a
Mhm.
half, 2? One and a half, 2
That's
cups. That's
that's
3.
3.
If I gave you, do we need to talk about that? Maybe not. If I give you 4, what's one and a half fours?
6.
6,
A
and that's what we
4
have,
and a
right?
2.
We have 2. So I'm actually going back up into the ratio table and I'm
Mhm.
examining some of the, and then 1 to 1.5, sure, 7. 7, what's one and a half sevens? Sure enough, that's 7.5. What's one and a half
Wait, 1 and a half
tens?
sevens? 1
Oh,
and a half
sorry.
fives.
Thank you. Thank you.
Uh-huh.
Misspoke. One and a half fives is 7.5.
Mhm.
What about one and a half tens? Pause, pause, pause. One and a half tens is
15.
15. Okay. What's one and a half 2/3? Oof. Well, it's be 2/3 plus half of 2/3. It's
Another.
1/3.
Yep.
And that's 1. So there's the 2/3 to 1. Cool. So we've got this other relationship happening. So we kind of have the within cups of peanut butter and within cups of chocolate chips. That's the within relationship. But we also have between cups between peanut butter and chocolate chips. We have that within, so or between. Blah, blah, blah. We have within relationships and we have between relationships. Sort of within the X's, within the Y's, but
Yep.
we also have between the X and the Y. There's a couple different ways of saying that. Cool.
Yeah.
So you just said that we could say the number of cups of chocolate chips, I'm writing Y, could be found equals by having 1.5, I wrote 1.5, times the number of cups of peanut butter, I'm writing X.
Mhm.
So if I were just to say that with the Y's, it would be Y equals 1.5X. Now
Mhm.
I could just go throw that in a graphing calculator, or I could plot it by hand. I threw it in a graphing calculator. I'm actually looking at that graph right now. Listeners, if you get a chance, you might just do that. I'm looking at a line. And sure enough, on that line, it goes through the point 1, 1.5, and it goes through the point 2, 3. And so we could find all those points on there, but we can also find that unit rate, that rate of change in the line y equals sort of mx. And the m, that slope or that rate, is what you said. It was interesting when you said, well, we got the 1. And bam, as soon as we have the 1, we do have that unit rate. So it's kind of nice that we can see both of those. There's an 8th grade standard in many states that I could draw the triangle from the origin that goes from the origin up to the point 1, 1.5, down to 1. I don't know if you can picture that. So in other words, the point 1, 1.5, if I draw a triangle from the origin to it and down, then that's going to be similar to the triangle if I go to the point 2, 3 and draw
Right.
that triangle to the origin. And now I'm talking about equivalent rates of change based on similar triangles, which is a lovely standard in many 8th grade classrooms. Kim, it's also interesting to me when I read Susan Lamont's Teaching Fractions and Ratios for Understanding that then we could look at all of those equivalent ratios that we had. So we had 2 to 3, 4 to 6, 1 to 1.5. We could look at all of those ratios as an equivalence class. Well, equivalence class, that's abstract algebra. That's the first time I ever heard that term. And let's be really clear. When I took abstract algebra as a non-mather, as a mimicker, oh my, I understood so little of that class. Now that I've been mathing, so much more makes sense to me. And when I first saw a bunch of equivalent ratios graphed, and then the fact that they lie in a line, and that line describes the equivalence class, I was like, that's what an equivalence class is? And a lot of things came together. And anyways, that's sort of brilliant. I would invite everybody to consider that what we've just done is build proportional reasoning by dealing with 2 cups of peanut butter to 3 cups of chocolate chips with these equivalent ratios by scaling in tandem and kind of using those within relationships. And then we're starting to transition to functional reasoning when we start to look at the between X and Y relationship and when we write the function to represent that. I'm not going to really call that robust functional reasoning yet, but we're definitely heading that way. And so that this is a moment in our sort of standards, our curriculum, our teaching, where we can help bridge from proportional reasoning, having built that proportional reasoning into functional reasoning. And I don't know about you, but when I was a student, I just skipped proportional reasoning. I didn't build any proportional reasoning at all. I cross multiplied and divide. And when I cross multiplied and divided to solve those proportions, I used an algorithm. So I wasn't even using multiplicative or additive reasoning to do
Yeah.
any
Yeah.
of, well, maybe it. No, I was just recalling facts. But here's a way, it's not the only way, that we can actually build from proportional reasoning into baby functional reasoning. And we're looking
Yeah.
at the function y equals 1.5x.
You mentioned at the beginning that you maybe got some pushback, that was raising some ideas. You say more
Yeah, I
about that.
appreciate that. Yeah. So in some of the work that I've done talking about proportional reasoning, I have focused on the within relationships. So scaling in the table I have, it's vertical. So scaling from 2 cups of peanut butter to 4 cups of peanut butter, therefore then scaling the 3 cups of chocolate chips to 6 cups of chocolate chips, and really helping build the proportional reasoning. Help me within. I have to think about which one within the peanut butter, and then scaling in tandem within the chocolate chips. I've really I've done a lot of focusing on that work, and the pushback I got was, when are you going to work on that between relationship and write the function for that proportional relation? And I kind of had to grapple a little bit with why I have done less work with that in a proportional reasoning workshop. And what I had to grapple with is it proportional reasoning or is it more functional reasoning? And so where I've landed, it's the bridge. It is absolutely proportional reasoning. And when we reason with functions, often we're going to reason proportionally, definitely not always, but that's a part of, right? It's nested within, it's built on proportional reasoning. And I think when we write the equation that represents that proportional relationship, that's bridging from proportional reasoning to functional reasoning. And somebody might say, but it's a function. I'm like, I know, but it's like proportional. And somebody might say, no, it's proportional reasoning. I'm like, I know, and it's bridging towards functional reasoning.
It feels like laying the groundwork along the way, and maybe not calling it out specifically like this is the work that we're doing right now, but asking the questions a little ahead of time, or wondering and noticing and being curious about those relationships just means that it's not brand new. It's not starting from scratch. When you're doing the work on a ratio table, you're getting kids to make sense of the relationships but between within going down or across the ratio table
Within because
within.
it's within each kind of.
Okay.
Yeah.
But then when you can just turn your attention towards, let's look at this a slightly different way, it doesn't feel brand new. It just feels like you're asking more questions. And I think when we talk about, even with a younger grade, talking about multiplication division, sometimes we will work with multiplication problems on a ratio table. And then we say, what about division? What if I ask you this division question? And because they've already made sense of a ratio table and how to make use of a ratio table as a tool, then you ask them a division question. They're like, I can tackle that. So I feel like this is kind of in the same way that you're making relationships more visible, and they're thinking proportionally leading into some functional reasoning.
Yeah, and let me just make one other point that I really wish we would make early, so that then later this was kind of built. I brought up earlier that I have the point 1 to 1.5 on that line, and I also have the point 3 to 3 on the line. We wrote the equation as y equals 1.5x, but we could also write that equation as y equals 3 divided by 2x.
Mm-hmm.
We could also write that equation as y equals 6 divided by 4x.
Right.
And maybe I would do the 3 divided by 2 since it's sort of quote unquote simplified. But that it gives us different information. Like the 3 divided by 2 gives us information that is maybe equally as valuable as the 1.5 to 1. And it also keeps, how do I say what I'm thinking? It keeps the notion alive that slope is a ratio.
Mm-hmm.
So when we say the slope of that line is 1.5 or the slope of the line is 4, I hear Garland Lincolnhoger in my head right now saying slope is a ratio. So if you're going to say the slope is 1.5, you got to say 1.5 to 1.
Mm-hmm.
Or if it's, but then if it's if the slope is 3 to 2, then you can say it's 3 halves. You can say it's 3 to 2. Like by writing the rate of change as a ratio, you keep alive that it is this ratio of the change in y to the change in x. It's not, slope isn't one number, it's a ratio. Does that make
Right.
sense?
Yeah, absolutely. I can tell you that when my youngest was graphing, he loved when the slope was in a fraction form, because he's like, it tells me exactly where to plot that. And so, we had to have conversations about when it says 1.5, that is also a ratio that you can graph. But that felt more to him like a thing to do, not
not reasoning
easier
about the
graphing.
ratio, not
Yeah.
reasoning about the ratio of the rise to the run, or
Yeah.
the
Yeah.
difference in the y's. Oh,
Mm-hmm.
that's interesting.
Yep.
I could see that in him. I love the fact that he understands so well. That's cool. All right, so everybody who pushed back on me a little bit about not going into that bit of functional reasoning with proportional reasoning, you're right, and so am I, and it's all connected. But it was good work, and we'll do more of that. We'll keep doing more of that. Nicely done. All right, y'all, thanks for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. And if you're a leader, school leader, we would love to talk to you about how we work with schools and districts. And let's keep spreading the word that math is figureoutable.
Thank you for listening and making math more figure-outable.
To learn even more about making math figure-outable and how to teach it that way, join us for our free challenge running September 3rd through 5th.
All you need to do is sign up and show up. Register at mathisfigureoutable.com/challenge.
That's mathisfigureoutable.com/challenge. Looking forward to seeing you there.